Pluto is a remote and confounding, more unassuming planet that was once a piece of our solar system's planetary assembly. However, later remarkable declarations by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning revelation. They proposed that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the repercussions of such a massive event? Are we witnessing a fascinating cosmic anomaly? Or is there more to this looming celestial confrontation? Join us as we explore the potential consequences of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet partly due to its unusual orbit, remains a subject of interest and research in the astronomical community. According to recent calculations by leading scientists, Pluto's orbit is dangerously close to Neptune's. Both Neil deGrasse Tyson and Michio Kaku have raised alarms about a possible dangerous collision between these two planets, which could pose a significant risk to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike that of any other planet in our nearby planetary assembly. It takes an astonishing 248 years to complete a single revolution. Since its discovery in 1930, it hasn't even completed one full orbit. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, tilted at 17 degrees to the ecliptic plane. Pluto's trajectory is significantly more extreme compared to other planets. This inclination and elongated nature add layers of complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its crossing point with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to understand its peculiar path. Unlike planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricate design of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem illustrates how the orbits of Neptune and the Sun's gravity interact in a complicated way. Terms like libration and resonance, along with VSK oscillation, are key to solving this puzzle. According to astrophysicists, what keeps all planets in their orbits is a libration. In the specific context of Pluto and Neptune, this term suggests that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Resonance libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another significant aspect of this equation is the VSK oscillation, named after researchers von Zeipel, Kozai, and Lidov, who studied how objects move in space. It describes how three celestial bodies like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling influences how they move. For Pluto, the VSK oscillation helps us understand why its orbit around the Sun is so unusual. Despite its seemingly chaotic path, Pluto's orbit remains stable for an extraordinarily long time, billions of years. This means Pluto's journey around the Sun has a kind of order to it, even if it appears unpredictable at first. Predicting cosmic events, especially when they involve erratic orbits like Pluto's, presents significant challenges. The inherent complexity of these systems means that long-term predictions are often fraught with uncertainties. While mathematical simulations provide a powerful means to understand and predict the future paths of celestial bodies, they also highlight the limitations of our predictive capabilities. Any minor error or deviation can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the turbulent nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto serves as a reminder that our knowledge of the cosmos remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can have far-reaching effects on the stability and behavior of other bodies within the system. So why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite all these intricate forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers an intriguing perspective on the mysteries of our solar system, particularly the captivating case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's interest in the uncharted realms of space. Tyson's stance on Pluto's reclassification is grounded in the ever-advancing knowledge of our solar system. He sees the reclassification not as a demotion but rather as a significant shift aligned with our developing understanding of the numerous bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He views the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. Similarly, Michio Kaku, another esteemed physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often chaotic forces that shape our universe. Kaku is known for his ability to connect complex scientific ideas with visionary concepts, making him a valuable voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's perspectives on Pluto and its orbit emphasize the need for ongoing observation and advanced modeling to understand these cosmic intricacies fully. Foreseeing and comprehending potential galactic occasions, he sees the communications between divine bodies as a significant area of study, both for scholastic purposes and for practical implications. The expected crash between Pluto and Neptune, for example, isn't just a theoretical situation but a reflection of the dynamic and often violent nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. His perspective highlights the importance of being prepared for the unexpected in space. Kaku suggests that the more we understand the forces at play, the better prepared we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's views converge on the idea that space is an arena of immense revelation and that our current understanding, while substantial, is still limited. Their emphasis on the need for ongoing exploration and advanced modeling reflects the evolving nature of space science. They underscore the importance of not only understanding celestial mechanics as they are now but also anticipating how they might change in the future. The potential impact scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It emphasizes the need for effective scientific inquiry, advanced technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, embodied by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that, for the foreseeable future, the orbits of Pluto and Neptune remain stable due to their mean motion resonance and the various gravitational forces acting upon them. Consequently, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities of potential perturbations in orbital dynamics still mean that astronomers should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they may pose. While the possibility of a Pluto-Neptune collision is largely theoretical and deemed improbable with current understanding, it highlights the importance of continuous research and observation in astronomy. Advances in technology, including improved telescopes and computational models, will help astronomers refine their predictions, ensuring that we stay abreast of the dynamic and ever-changing nature of our nearby planetary system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both underline the need for ongoing investigation and a flexible understanding of our universe. The potential impact scenario, while showcasing the dynamic and complex interactions within our planetary system, ultimately reminds us of the vast yet still incomplete gaps in our understanding of space. Through continued research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe. Pluto continues to captivate scientists and space enthusiasts alike with its distant and enigmatic nature. While its status as a dwarf planet has long been debated, its orbit and unique characteristics keep researchers engaged. Recent developments have once again placed Pluto in the spotlight, with the possibility of a gravitational interaction between Pluto and Neptune becoming a focal point of attention in the space community. With Tyson and Kaku bringing this subject to the forefront, the discussion surrounding a potential Pluto-Neptune collision is bound to spark further interest and investigation. The study of these intriguing celestial bodies holds the promise of uncovering new insights into the mechanics of our solar system. As we peer deeper into space, the dynamic and unpredictable nature of our cosmic neighborhood only emphasizes the need for vigilance and ongoing exploration. While the potential interaction between Pluto and Neptune remains a topic of scientific interest, it is essential to consider the broader context of space exploration and the methodologies used to study celestial bodies like Pluto. The discovery of potential risks, such as a hypothetical Pluto-Neptune collision, serves as a stark reminder of the immense complexity and unpredictability inherent in the universe. It highlights the intricate mechanics at play within our solar system, where even the most seemingly stable orbits may harbor hidden vulnerabilities. This notion draws attention to the sophisticated tools and techniques astronomers and physicists use to understand the motion of celestial bodies. One critical tool used in such studies is numerical simulations, which allow scientists to predict and model the behavior of planets and dwarf planets over extended periods. By inputting known parameters, such as the mass, velocity, and distance of celestial objects, these simulations can project potential future movements and assess the stability of orbits like Pluto's. Such models often rely on powerful computers and advanced algorithms to process the immense data and complex calculations required. This approach is especially useful when studying objects with unusual orbits like Pluto, whose path around the Sun is distinct from other planets in the solar system. Moreover, the role of gravitational interactions between celestial bodies cannot be overstated. As mentioned, Pluto's orbit intersects Neptune's, and the gravitational pull between these two bodies could, in theory, lead to unpredictable outcomes over extremely long time scales. However, due to the resonance between Pluto and Neptune, their orbits remain locked in a stable relationship. This gravitational resonance ensures that even when Pluto comes close to Neptune's orbit, they never collide. The physics behind this resonance is fascinating, as it demonstrates how the subtle forces of gravity can synchronize the motions of two distant bodies, preventing catastrophic events like a collision. At the same time, there are still questions about what other factors in the solar system might influence Pluto's orbit. For instance, the presence of other planets such as Jupiter, Saturn, and Uranus could potentially disturb the delicate balance that keeps Pluto and Neptune in their stable orbits. These massive planets exert their own gravitational forces, which could cause minor changes in Pluto's trajectory. While these shifts are typically small, over millions or billions of years, they could accumulate and result in more noticeable changes. For this reason, astronomers continue to monitor Pluto's orbit carefully, looking for signs of any deviation that could indicate a future disruption. Beyond gravitational forces, the influence of the Sun itself also plays a crucial role in shaping the orbits of objects in the outer solar system. The Sun's gravity dominates the motion of all planets and dwarf planets, including Pluto. However, because Pluto is located so far from the Sun, the Sun's gravitational pull on Pluto is much weaker than on the inner planets. This means Pluto's orbit is more susceptible to external influences. For example, the Sun's varying energy output over time, such as during solar cycles, could impact the behavior of objects in the Kuiper belt, where Pluto resides. These subtle changes could affect the long-term stability of Pluto.